Oh, there's John Kulik. Okay.
Wonderful. Good afternoon from Montreal, where it's 1 p.m. in the Eastern time zone, and good morning, good evening, good day from wherever you are joining us in the world, and welcome to this technical webinar on fiber attach and technical progress within IEEE standards. This session will be recorded and available online after the event. For some housekeeping rules, if you are joining us, please mute yourself. And if you have any questions, please message Benjamin Crockett or myself, Matthew Posner, in the chat. I hear some echo, so I believe someone might already be unmuted. I asked that you try and mute your microphone as you enter the room. We have a number of colleagues from the IEEE Standards and the IEEE Photonics Society. Many of them are volunteers or in leadership roles. So if you are joining us, please put your camera on to say hi. And my name is Matthew Posner. I'm chair of the IEEE Photonics Society chapter of the Montreal section in Canada. I wish to start today by making a brief land acknowledgement from the place I'm speaking from. Many of us, including myself, are settlers, immigrants, and some are descendants of those forcibly brought to this land. And so it is our collective responsibility to pay respect and recognize that in Montreal, this is a traditional territory of the Mohawk, Algonquin First Nations.
Put stuff in the chat if you can't get to the Slido, or if you want to make.
And we are here because this land was occupied during history, so I encourage you to learn about the history of this land that you are now. So I salute to many of my partners who have contributed in the promotion of today's event. I give special shout out to my colleagues at Optonique, Maurice Lamontagne at the National Research Council of Canada, as well as a number of leaders from the Region 7 Canada, chairs of Quebec, Toronto, Ottawa, and Vancouver, and a special warm welcome to our colleagues from the IEEE Pittsburgh session, where our speaker is based today. It's 2 minutes past the hour wherever you are in the world, and we will be getting started soon. Whilst I'm speaking and introducing the speaker, I would be grateful if everyone can use the chat and type in your name, your affiliation, and where you're calling from today. Today, we have the pleasure of being joined by Mr. John Mazurowski, who is Director of the Electronics Manufacturing Center and Navy Manufacturing Technology Center of Excellence, located in Penn State Applied Research Laboratory, which is a center that began in 2021. Previously, John was the head of the Fiber Optics and Photonics Department, a position he held since 2018. John has had an illustrious technical career in manufacturing technology. He has held tenures as an engineer and manager, many projects in the manufacturing of electronics, RF, and photonics components, including in household names such as Corning Photonics Division, Avenex Biocontrol Technology, the General Electronics Laboratory, and Harris Communication. John has over 40 publications and presentations related to solid-state materials, electronics, and photonics, and holds 3 patents in the areas of design and packaging. He is the chair of the IEEE Pittsburgh Electronic Packaging and Electron Device chapter, as well as having held a number of tenures for leadership positions of the IEEE. John is a senior member of the IEEE and a member of other professional societies. He earned the bachelor's and master's in physics at Syracuse University, and I believe is a wonderful example of how we can have an exceptional career of service and technical accomplishments. So John, thank you for being with us today to share with us the recent work on the IEEE Photonics Society and the IEEE Standards Committee on your recently published white paper. Just for everyone to know, John has accepted to take questions during his presentation. So if you do want to ask a question, we ask that you raise your hand and or write in the chat so that myself or Ben can relay and signal your question to John. So without further ado, John, the floor is yours.
Thanks, Matt. Yeah, I completely agree that this could be kind of open dialogue. Those of you that are expecting any statements about cutting edge research, you'll get a few, but this is really to guide us through the preparation and path forward for this particular standard on fiber attach. I'd like to welcome John Zulik, who is the IEEE Photonics Standards Group lead. We're starting to talk more and more often because he's thinking of retiring and has asked me to assume his position. So welcome, John. Another kind of trivial piece of information is both of us had graduated from Syracuse University Department of Physics and know many of the same people of course, from from years ago. Many of them are retired or emeritus. So let's get started. This is kind of contents of the talk. Does everybody see the whole slide and nothing more? Being the presenter, you know, there's a lot of information missing, and I'm getting kind of a partial slide for some reason. So I'll just keep going.
You're looking good, John.
Okay, good. So we'll summarize IEEE standards, kind of the spirit of the organization, and then move into the subject of fiber attach with some background, the objective of our standard and white paper, and then a summary of what's in it. Just FYI, if you do a search on IEEE fiber attach standard, you'll probably stumble into it right away. It's not protected or anything. Then a path forward and how people can be involved. Okay, this is kind of a short presentation. I'm going to fill it in with some vignettes and stories. I hope you don't mind, and so feel free to chime in with your thoughts as well. The IEEE Standards Organization is an operating unit within IEEE that develops global standards. And many of you, being familiar with those, know that the standards are of very high quality. I come to the IEEE with a bunch of experience from the SAE aerospace division, where I ran the photonics and fiber optics committee. We issued a lot of standards. SAE is the largest standards body in the world, but has a very diverse collection of hundreds and hundreds of standards, mostly applicable to aerospace in our group. And so the path to developing standards there is very similar to IEEE. One difference is that the IEEE gives credit for the authors of the standards and the people that had a role in generating them. So we like that very much. The basis of IEEE standards is balance, openness, fair procedures, and consensus. You see that in kind of bullet number 2. And it's very neutral. And we have a lot of help along the way to make sure that the standard is useful to its users and complies with the IEEE Standards Organization standards requirements. Now, the Photonics Society also has an IEEE Photonics Standards Committee, which in parallel is underneath the IEEE Standards Association. The chair of that group is John Kulik. The vice chair is Yu Yuan, and then Raja Ahmad is the secretary. I'm going to make sure that I cite places where I get information, because there is not a shred of original content in this presentation. It's all from sources that are pretty well known. And this information was taken from an article written by Patel on the IEEE standards that contains some very nice observations about the standard generation process, which is on this slide. We initiate a project and write and submit a project authorization request to the IEEE Standards Association, and they judge the case for users and the need for a standard and the fact that it'll be necessary and sufficient to fill that need. And then we identify a working group. As I said before, the process is pretty open. So mostly by email or by contacting the IEEE Photonics group, you can directly become involved in writing the standard at whatever pace and amplitude you'd like to be. And it's up to the group to keep everybody, you know, within the navigational beacons and make the standard meaningful. Once the standard is drafted, it goes to ballot within the working group and gets submitted to the IEEE Standards Department, who solicits anybody that has an interest to submit their thoughts. After getting 75% approval, we go to the Standards Board Review Committee, who does a final review of the formatting and the information to make sure that it complies with the standard requirements. And from then on, standard goes into maintenance mode. It's funny that the SAE, where I come from, has a very similar validity period. I think it's 5 years and not 10 years, but you have to review every standard over a period of time to make sure that it's either up to date or you make sure that you revise it so that it stays up to date. Now, what we've done, what is published and what we're talking about today, is a white paper, kind of an engineering document about the issue of fiber attach, which is, as you guys know, very valid issue in connecting, in particular, photonic integrated circuits. And so that kind of outlines the span of the document that we're on the way to preparing. Okay, we're going to go into some technical stuff now. I really like these cartoons. In the upper right, we see kind of a picture of a wafer with maybe some reticles on it. The reticles, well, they all look fairly complex. Some of them are repetitive, and they're all of the same size, which is a kind of a cartoon in itself, right? And below it, a picture of a fiber cartoon. I like this picture, by the way. There's just a little contribution I'll make to vernacular, and that is that a standard fiber used as a flexible waveguide between assemblies and subsystems, and even metropolitan areas and racks and buildings, consists of glass, core, and cladding, then a coating, a strength member to add longitudinal strength, and then an outer jacket to protect it against outside scrapes, cuts, and abrasions. The coating is to prevent OH, or what they for short call moisture contamination. And a lot of times we see misnomers where somebody misuses the words coating and jacket. So this is what I consider to be the correct vernacular. And so on the left is a description, kind of almost why we're here, when transmitting optical signals between any device or between integration platforms. And I think you probably know what an integration platform is. It describes the whole device, and in photonics, it's very dependent on the base materials used, 3,5 silicon photonics, or 2,6 materials, et cetera, et cetera. So the internal waveguides that connect devices within a reticle or chip have a higher loss, a much higher loss than the flexible waveguide we know as fiber. So there's also a difference in distance within a reticle or a chip. That 1 dB per centimeter loss is only applicable over millimeters at best. So it's not a serious loss. And so we, in going through a fiber attach device, we avail ourselves of a very miraculous flexible waveguide, right? Something that's been optimized and optimized over 50 years to have very low loss and handle signals extremely well due to its symmetry and guiding properties. So the definition of fiber attach is when we connect between integration platforms or devices using optical fiber. And you'll see it's a little more than that. We're starting to get into extremely short connections that may or may not fall under this standard. But we require, as an industry, optical loss to be as low as possible. And we all know that this is one of the more serious problems we're facing in the age of integration, that fiber attached loss is quite high, and we need to work on that. At the bottom, there is this great paper that's just been issued called Roadmapping the Next Generation of Silicon Photonics, issued by some folks from Dream Photonics and Huckberg, John Bowers, and it's a fantastic paper. If you do a search on Krostowski Photonics Roadmap, you'll probably reach it. And not exactly using it as a reference, but just citing all the users in on this call, that it's a pretty good treatment of where we are in the world of silicon photonics. Oops. Okay. This is kind of a comparison of sizes without actually giving the sizes. On the left is information about fiber again, showing the nominal 10 micron core of a standard silicon fiber. On the top right is a collection of different waveguide designs, and suffice it to say that the size of the width of these waveguides might be as small as 20 nanometers up to maybe 400 nanometers, depending on the integration platform. So there's a 2 order of magnitude discrepancy to transmit light between a fiber and a waveguide in an integrated circuit, or vice versa. On the bottom right is a picture I found on the web of an overfilled square waveguide. Now, one big problem in high-speed communications, of course, is the symmetry of the mode field. And this shows a square waveguide that has a mode field that's roughly circular, very symmetrical, and so you avoid problems like polarization dependent loss and polarization mode dispersion, which are both somewhat of a problem in photonics, particularly having to do when you do functions other than just transmitting digital signals. Any questions about this slide? Okay, we'll move on. This is a interesting diagram. I got it from a presentation given by James Pond, who was working for Lumerical, which got swallowed up by ANSYS. And this shows the many functions that you do, that you incur when designing a photonic IC. There are physical structures, there's thermal management and heat flow, electrical connections, and photonic connections and devices. And one really cool thing about this diagram is that it illustrates some lessons we've learned over the past several years. One is that we've kind of shied away from using our electronic EDA tools to encompass photonic functions as well. I think one way in a systems engineering case to keep functions independent of each other, that's a good system engineering principle, keep subsystems, functions, allocations as independent as possible, is that you see heat flow is occurring both from conduction below, convection, and radiation above. The physical support is shown from the substrate below to an interposer to photonic ICs and perhaps electrical components. Most notably, the electronic functions seem to be pretty separate from the photonic functions. Did I say that right? Electronic separate from photonic, rather than integrating both functions at once. We tend to put either together separately and then merge the two via lamination or mounting, as shown in this picture. So I thought it was pretty nice, and I hope you like it. Yeah, this is going to be one of the last pictorial slides in the presentation, and it's kind of a picture of maybe where we are in terms of fiber attach. In the upper left-hand corner, there are all the butt coupling methods that generally go to sides of devices that show just a fiber that's joined through a little bit of free space to a device, one with a ball lens. That lens could also be a spliced on grid lens to serve the same function. Then a Self-Hawk lens, a half sphere. That geometry can be added to an end face, or can even be formed using a fusion splicer. Those of you who are into sophisticated fusion splicer recipes, and then a ground taper, a grinded taper, or a pulled taper. An adiabatic taper is a really nice way to go over a couple of orders of magnitude without causing asymmetry. That is, transmitting one way versus the other. I should say directionality. In the middle at the top, we see a grating coupler, a vertical fiber coming down on a grating that aids transmission and decreases loss. In the middle of the middle, we see a V-groove array that is used to set the position passively of an array of fibers, usually in a ribbon. We started out with 250 micron spacing between fiber cores, and I think now there's 200, and maybe is it 123 for some of the smaller fibers. Hopefully it won't get too unmanageable with many fiber to fiber diameters, but that's self-aligning technique that's used very common, and it gets you nominal performance. The most interesting thing that's happening in terms of fiber attach now, and I alluded before to going from chip to chip in addition to fiber to fiber, are two methods of using very short fiber transmission methods. Vanguard Automation is building systems using a two-photon interaction. It was about maybe 5 or 8 years ago. I saw a paper from a university in Europe showing this two-photon interaction that could be used to, in 3 dimensions, write photonic structures. It's come full circle now to perhaps TRL 9, technical readiness level 9, for those of you that don't know TRL, many companies are using this method now, and you can see the adiabatic taper method used between fiber cores and waveguides in an integrated circuit. I saw another paper, I believe it was in EE Times just a few weeks ago, from Lessingers, which is a Chinese company, and it shows something that looks like little gold ball bonds, ironically, but it says that they're fibers that are connecting end faces directly. And the article I saw didn't mention too much about exactly how it was done, but the fact that the quality of those interconnections is pretty acceptable. On the right-hand side are some vignettes, one from Paul McClellan, which he does some blogs from Cadence, EDA company, and says, hey, there are 3 ways to do fiber attach. One is passive alignment, where the assembly equipment positions very precisely and aligns a fiber to a ship without using feedback at all. So you're going to spend a lot of money on precision, things like reproducibility, angular as well as planar and longitudinal or latitudinal alignment. Active without power, some feedback is allowing dynamic placement of a fiber in relation to a chip or a chip relation to a fiber to get even more optimized alignment. And then he's saying that you can do power on alignment, where the photonic integrated circuit is powered and with a mechanism gives feedback about the quality of alignment, which is the most apt to give optimum results. And back to the paper on the photonic or silicon photonics roadmap, their statements. This is, by the way, the very last statement in the paper about things that are going to happen in the near future. And it says that we're going to have a typical insertion loss dropping to under 0.5 dB per junction. And way at the top, a statement from Global Foundries on Silicon Foundries that fiber attaches the secret sauce. So the theme of this slide is that, hey, the industry acknowledges that this fiber attach is a universally accepted problem that we're all working on, either separately or together. And so the Photonics Standards Group in the IEEE is following this. And I don't think the intention is to make a standard that everyone must comply with. It's to make a set of requirements that can be used to assure interoperability between all organizations that are involved in this transmission of light between ICs and fibers or otherwise interconnect devices. So this is probably technically the most important slide of the presentation. Any comments or questions? Feel free to chime in. By the way, I see Ben Fasano in the attendees. Hello, Ben.
Hi, John.
Ben was a guy that had considerable contributions into the white paper, and I was at a conference or a meeting, and up comes this guy. We're both drinking cups of coffee, and he says, I'm Ben Fasano. And it's like, wow, through all these teleconferences and everything, it's kind of wonderful to meet somebody face to face. Anyway, Ben has experience with IBM and Global Foundries and is a really good guy to run ideas by. Very candid, and thanks for your contributions. And
Hey,
before
John, this is Hey, John, this is Randy. And
Randy, yeah, Randy Renard as well. Yeah.
I think you're hitting it. This is extremely helpful. So, and I just wanted to thank you.
Yeah. You're welcome. And anybody that's involved in the committee, I'll recognize you in just a minute. This was an extremely good group and is going to continue to be a good monitoring of the pulse of the industry, where we're going. Okay. Next slide, we're going to go to the last 2 sections of the contents that talk about the standard development.
Before you jump forward, there was one question which came through from Lewis Hart in the chat. He was asking, what are the blue cones in the Vanguard automation imaging figure that you present?
The blue cones.
I think pretty referring to the fiber attach between if you go forward on this one, the bottom picture, I think these are you see the blue lines. I think these are those polymer waveguides from the fiber to the waveguide.
Yes.
Could you confirm?
Yes. And thanks for asking that question, because um, those are tapered dielectric waveguides that are made using a two photon interactions that draw these things in 3 dimensions. It's remarkable. And thanks for asking that so much, because, you know, just like the invention of fiber, when I talk about fiber itself to people, I say that the basis of fiber is 5 miracles. And these transmission lines, just using light printing in 3 dimensions in dielectric, I think has its own set of miracles, right? Does that answer your question? Okay, we'll assume yes, and we're going to move on to the going through to the standard summary of the and where we've been and where we're going. So this is directly from the standard, the wording of the objective, and you can read through it, but the intent, obviously, like I said, is not the standard that requires compliance. It's a matter of communication so that we can assure at the bottom, you know, compatibility, efficiency, and interoperability. That's the key. When you say you're doing something to a potential customer or a supplier, we hope to engineer or develop a standard that is a pipeline, in particular, you know, for other people that would like to use a standard for fiber attached, for instance, in multi-source agreements, MSAs, etc. And we'll see where it goes from there. Right now, I like to call it the Wild West era, where there are many different approaches to doing fiber attach, and some folks say they've succeeded and they've standardized on different methods, but there's no overarching system of communicating between groups of suppliers what that requires, or what it conveys, and that's what we hope to accomplish. Okay, progress so far along the path for the development of the standard. We've issued this white paper, and like I say, if you do a search, you can Google IEEE fiber attach white paper, and you'll get it. It's in PDF form, released in October of 2023, and I think early in 2024, the IEEE Standards Association approved its publication, and now it's out there on the way to being used and being commented on by people in the industry. These are the people that contributed to the white paper. I'd like to specifically cite John Kulik, the IEEE Photonics Standards Committee chair, who has been a steadfast optimist and knows how to keep us facing the same way down a course. And Wei Jiang from Nanjing University. Now it's he wasn't able to participate in the call because it's the Chinese New Year and it's probably 1 or 2 o'clock in the morning. So I don't blame him for sending his apologies. And then there were pretty considerable communication or contributions from most of the people on the list, and some of them are in on the call, Randy and Ben in particular. Okay, and this is one nice thing about IEEE standards, that they give credit to authors. Many other standards organizations, probably for reasons of liability or possible proprietary reasons, the contributors stay anonymous, and that's good too. Oh, another person I'd like to give credit to here is Dick Oddie. He was one of the two individuals that is working on the heterogeneous integration roadmap. It was 10 years ago, I was introducing the idea of photonics to IMAPS, you know, the Society of Assembly and Electronic Packaging, you know, communicating to them that, hey, under the guise of heterogeneous integration, you're going to have to handle things like digital and analog and photonics and maybe fluids at the same time. And Dick was very helpful, as long as Bill Chen, I think, in holding a series of roadmaps, and made a pretty significant contribution to the photonics end. There is a heterogeneous integration photonics roadmap that's published, and they continue to maintain it. Okay, you know, one of the first things we did had to do with due diligence, and we collected as many standard generating organizations as we could to see if there were any duplications of effort. I think we may have forgotten a couple here. I know INEMI is one organization that works in photonics, but you know, we didn't really find any duplicates, and the substantiation of those findings is on the right side. Enough said, but you know, we think we're in a unique position to contribute to this huge issue, and you know, perhaps under development of the standard, there might even be some avenues for support from further work, not from the IEEE, but other organizations that are witnessing the standard development process, and see snippets of technology that can help make incremental progress, right? This is not a strict table of contents in the white paper, but kind of a list of subjects, the relevant standards, the rationale, using silicon photonics as the primary integration platform. And I say that because much photonic integrated circuit development occurs in silicon photonics because of its compatibility with the CMOS manufacturing process, you know, very mature. A summary of standardization literature. There are references in there that are very credible. Overviews of current and future fiber attached technology. I would say that we'll embellish that a lot more as the standard gets developed. We have a chapter, but it doesn't go into great detail about where we are and where we're going, but much more to come. Directions for standardization, then definitions for performance overall, and optical performance, and technical aspects of fiber attach technology. Another piece of trivia, just so you guys know, is I always go through the battle myself and with my proofreaders about whether you put periods at the end of phrases in a bulleted list. And here's the answer. I believe it comes from the Chicago Manual of Style, and that is, if the bulleted items resemble sentences overall, you use periods. If they're just words or phrases, then you don't use periods. So there, okay. Performance aspects. Now, the white paper goes into pretty great detail about specific metrics to be communicated when you specify a fiber attach method. And here's kind of a summary of what they are: is how much optical power do you use in transmitting fiber, and in particular its symmetry. Is it symmetrical or asymmetrical? Then mode field matching. both in terms of the dimension and acceptance angle, and those can play a big part in the symmetry, right, of transmission. If you're going abruptly from a large mode field to a small mode field, you're probably going to use some power, lose some power. Back reflections and multipath can affect devices that are connected along the way. In particular, sources that you need to have very, very clean to do quality work in the optical performance domain. Polarization, T or TM polarization play many times key roles in performance. The spectral range and the bandwidth. Keep in mind that in photonics, we're modulating optical carriers. And so there is the ability to handle great spectral bandwidth of signals. There was a paper published, some time ago that said, we don't need WDM, we don't need multiple carriers or cores. We need one optical carrier that handles signals of optical bandwidth. And this theoretical case was made by this guy, and I'm not sure if it's too prolific, but it's a very interesting idea. One carrier with almost infinite bandwidth, right, for modulation. And then, of course, power limitations due to materials and in particular power density. We talk in terms of handling aggregates in photonics of, hundreds of milliwatts, and then we move up to transmission of high power signals and in the fiber laser domain, perhaps, tens of kilowatts of signals. And so going through an end phase, there's an extreme power density in the mode field, and those can cause some deleterious effects. This is, again, the number of functions that we consider when we work on photonic integration problems, and also are superimposed on the technical aspects of fiber attach, that there needs to be mechanical support. We need to pick appropriate materials that relate to performance and all the other features, specifically the environment in which it's used, the optical performance itself of the fiber attach, the mechanical structure and strength, and environmental aspects of the intended application. You may know this, me that's working on different platforms anywhere to from benign to space, understand that in photonics, many times the hardware that's used in specific environments is not compatible even with hardware that's used in other environments, just simply because cables, connectors, devices are optimized for a particular environment. And you can make big problems for yourself if you, for instance, use benign cable in an aggressive environment. It'll kill you in terms of being successful. Okay, I think we're just about to the end here. So this is the path forward, and I think the two phrases in the end speak about the destination for this standard on fiber attach that really concentrates on interoperability between chips, devices, subsystems, platforms. I keep, when I consider a new application, I keep thinking, well, can this be integrated? Can I buy 1,000 of these if I make a wafer with 1,000 reticles in it or 1,000 devices? And what's that going to do for my customer? And looking forward to the day when we can all do that in this industry and connect things together with this flexible waveguide we call fiber, and not worry about the attachment or the loss or the rigidity or the reproducibility. Okay, I'm really surprised that we used up 40 minutes of a talk. So thank you very much, and like to entertain questions. Oh, wait a minute, there's one more slide here that talks about how you can participate. If you do any search on IEEE Standards, IEEE Photonics, you'll probably stumble on a page that has to do with standard development. And to be involved in this standard in particular, you can go to the website in the center of the page, and it'll lead you to communicating with the individuals involved. There are dialogue boxes and also emails with everybody that can provide you an on-ramp into standard development. And it also includes lists of the current standards that have been published and projects that are underway in the Photonics Standards Committee. So now let me say thank you very much and ask for comments or suggestions.
Thank you very much, John. And we do have John for another 30 minutes until the hour. So if you do have questions or comments, please mute yourselves and address them out loud, or we can relay them for you from the chat. And I'm seeing a few comments, I think, on the predicament and how to use bullets have been put forward by Randy. So that may be taken lightly, but there's certainly a number of submittals which are being brought forward. Randy, would you like to say a little bit more about these submittals that you mentioned in the chat so that people can have a bit more context and background, please?
Yeah, so the IEEE NMDC 24, that's the IEEE nanotechnology kind of flagship conference, and we have nanophotonics related topics, nano devices. It's a material device conference. It's in Salt Lake City in October 22nd, 23rd, 24th. So if you're interested, there's the link. So we certainly welcome submittals. And in John's fine presentation kind of talks about some of the devices. So I appreciate that.
Thanks, Randy.
Thank you.
Yeah, I've got a question just straight up to John and obviously to the audience. This is Ben Fasano. One of the things that struck us in many cases during our meetings, which went on for probably 18 months or so, trying to get this white paper together, was the inability to connect to people that are actually going to either benefit or hopefully participate deeply into developing the standards, from the equipment engineering manufacturers, material suppliers, the assembly houses, and this is often the case now where it's a hybrid microelectronics and photonics place where everything gets put together. There's no longer, specialty companies that just do photonics or optical assemblies and microelectronics. What we ideally need is a lot of participation from the people who would be expected to try to help to not only define, but then meet and then extend the capabilities for some of these standards. I'd put it out to the audience how you can participate in trying to get your company on the list of people that are making the cut for setting these standards, and also, being able to look in the future for what additional development would be needed in your research and development activities. So John, can you just maybe go back to that aspect of how to get involved?
Yeah. Let me see here. I'm gonna, you can do a search on IEEE Photonics Standards, or use this website explicitly, and it'll take you to pages where we show it's the IEEE Photonics Standards Committee webpage, very nicely put together, and you can get to the officers, in particular, projects underway all have working group chairs, and it gives you their contact information. It's very open and collaborative. So if you want to get involved, even for a little role, even if you want to monitor progress, we're going to try to draft you into a contribution, even if you're just there to monitor. Please get involved. This is a great group. I'm really, really happy to be taking part.
Hey, John, if I can, I just wanted to mention, so the industry connection, or ICADE, was where this fell under, but yes, the standards, as John Kolnick, it's a standards committee, but the ICADE group has some related activities people may be interested in. So it's IEEE ICADE, ICAD. I put that in the chat.
Well, thanks, Randy. Hey, and I liked your statement about the subject and predicate. In what I saw, there was no mention of a subject and predicate, and I do kind of look at what I write to see if each phrase that resembles of a sentence has a legitimate sentence structure, but many times they don't.
Thank you. Any more questions from the audience?
Yes.
Alain Villeneuve, calling from Montreal. Great to see you. The floor is yours.
Yeah, thank you, Ed. First of all, thank you very much for this initiative. It's very important. I worked a lot in integrated optics back in the last millennium, and then I went into fiber lasers. And when I came back, I noticed that there was no effort to standardize on anything. And for smaller volume application like biophotonics or quantum or stuff like that, having a standard is essential. So this is absolutely great. I think I will try to join and see if I can help. But I do have another question. Is there any efforts to come up with a few standardized package that could include, fiber, that could include some RF and DC signaling, to reduce the cost of the packaging? Every time I ask that question, I've been shut down. So I'm just asking if you guys see any needs or any work toward also a standard on package or standard packages. Thank you.
Wow. That's a really good question, Elaine. Thanks.
If I can, so the IEEE CAS SASD actually is a group that's contemplating that right now, potential powers, and being a member of that. And that was one of the things that I'd started talking about. So yeah, I know that there's some other WGs that have some adjacency. So yeah, there is some work out there.
Thank you.
Yeah, I hate to say it, but one of the most well-developed standards was the 14-pin butterfly package, and very expensive, very rudimentary, but it's one of the things that we can hang our hats on. And from then came on MSAs that describe transceiver packages. But aside from individual efforts at designing things like photonic microbenches or photonic benches, not much effort. And I have a challenge for you, that we know how to get lots and lots of power in to a fiber from a fiber laser, but try to get it out to be used in free space other than spreading it out. People that have high power fiber lasers don't really have connectors, do they?
Well, yeah, that's a good question, and we can talk offline about that.
Yeah, feel free.
Yeah, that's I'm a fiber laser expert, so we can talk. But yeah.
John, in that same vein, and thanks for asking that. I mean, the IPSR roadmap discussions, which I was at MIT a couple months ago or so, they've recognized that there are so many different interface connections, as John went through earlier with, edge coupling, butt coupling, the written waveguides or wire optical connections. I think that's going to eventually shake out, but yet there will still be some niche applications where there's no other option but to use that. And I think where it's going to get really down selected is when the powers start to kick in. And for instance, you can't utilize top space for doing any kind of cooling like they often do with flip chip, because you've got to cut out some substrate, or you've got an extremely complicated optical guiding system for lenses and things that have to be put at the fab. And that's going to eventually have an extremely broad application space or an extremely narrow application space. Some of these will fall off of the potential implementation. So you can drive yourself nuts if you try to find a standard for every one of those, and that's why we were trying to get something that would just sort of be a general spec for things like losses, back reflections, all those other sort of things that John briefly touched on.
No, I agree with you. It's a chicken and the egg type of things, but I was also mentioning a few standard package, depending on the applications and everything. But if there's no standardization between the fab and the packaging houses and everything is going to be custom. It's going to be very expensive. And then you're going to have this big mountain to cross before you can get any devices. So yeah, it's a chicken and the egg thing. Anyway, so that's, yes, thank you very much.
And I might say if you study any of Clayton Christensen's articles on product development, you will see that there are what he calls bases of competition. The first one is that isolated sources develop something that serves a function. The second phase is that function is done by somebody very reliably, and so everybody looks at that method. The third is the function is accomplished, it's done reliably, and it does it with amounts of sub-functions that are useful to customers, product frills. And then the fourth is commoditization, which none of us will like. That's when the basis of competition is cost. And we're in the first stage. There's a tremendous amount of progress being made per dollar spent on research, and isolated sources have optimized systems of fiber attach, and will hopefully start converging, hopefully we'll come up with some kind of some general ideas about what can be done for fiber attach, to more thoroughly answer your question, Elaine. But Christensen's work on product development is very interesting reading if you have any spare time.
I'll take notes.
Thank you, John. Thank you, Anna. And we are getting close to the hour. So if I may say some final words to close this meeting and credit John, I think, maybe misquote him, but we are in the Wild West era, as many different approaches for doing fiber attach. And I'm taking away that the key is communication, maybe not compliance, for building standards of pipeline as we start looking towards more integration between fabs, design houses, packaging, and different suppliers. So thank you all today for participating in this webinar and joining John, who shared with us recent work by the IEEE Photonics Society and the IEEE Standards Committee on their recently published white paper. I think you have met people today, and they will be able to keep connecting to engage with this working group in the future. There's certainly a need for further engagement and keep contributing towards technical advances through the Standards Association, the Photonics Society, or your local clusters and research and innovation partners. So With that note, thank you very much, John, again, and for everyone for participating on this call. And we wish you a great rest of the day, or start of the day, or end of the night, wherever you're recording from in the world.